So here is a concrete example of a linearization problem. The function is y equals x squared plus 1. This is the required Mathematica syntax. You can get help with this using the classroom palette if you wish, or you can memorize it, but you have to use the proper syntax for any program you use. So f square brackets x underscore close square brackets colon equals. That's just the basic syntax for defining a function in Mathematica. Here's the plot statement for that function. We're going to plot f of x from -4 to 4 in black. This p1 equals in the front of that is naming or saving the plot to a variable so we can display the plot by expressing p1. This next line is defining the point of tangency, x0. We would also like to plot the point on there, so this is the way you plot points in Mathematica. It's called list plot. And we're list plotting x0, f of x0, which is the point that we would be using as the point of tangency. Also in black, that's named p2. Now, the show command would allow us to put both of those plots together, and here's the curve plus the point. The semicolon up here in the plot point suppresses the plotting, the actual plotting of that single point, so we aren't cluttering up our document with extra plots that we don't need. This is defining another function called L of x, the linearization of the function f is y0 plus the slope times x minus x0. And here's the plot of that linearization from 1 to 3, since we don't need the whole thing, since we're only using a little chunk of the tangent line. And we're going to plot this blue at medium thickness, semicolon, again suppressing that plot, but naming it P3 so we can draw all three of those one upon the other, plot 1, plot 2, plot 3, and here's the function and a little chunk of the tangent line at the tangent point. Here we're going to define the allowable error in using the tangent line rather than the function itself as 0.4. So plot 4 is plotting f of x shifted down by 0.4 and up by 0.4 to create a band of allowable values before we get beyond the error that we will tolerate. And they're both done in thin red lines. The error at any given point is the value of the linearization, which is the blue line. Subtract from that the value of the function, and that will give you the corresponding error at that point. At the tangent point, there's no error. Out here, as you move further away, in this case, the blue line is much lower than the black line, and it's outside of what's allowable in terms of what the lower skinny red line indicates. So what we have to solve is an inequality which says what are the values for which the error as a function of x is less than the 0.4. Now, if you paid real close attention in pre-calculus, you might be able to solve this quadratic inequality. It turns out that that's about as far as you're going to get, because once it gets to be more complicated in the quadratic, it would be very hard to solve that by hand. You'd end up with numerical methods, so you might as well be using technology, because you are going to have to use technology. You can look up the help information in Mathematica, and you'll find out for solving inequalities, sometimes reduce works. Reduce the error being less than 0.4. And somehow it couldn't solve that with reduce, but it did something else, which don't care as long as it did it. And there are two solutions, one for the upper curve, which has no intersections, and one for the lower red curve, which does. These are the two solutions for the lower, where the blue line intersects the lower red curve, and that's between 1.367 and 2.632. The other one are the imaginary values for the upper curve. So defining x min and x max as the boundary in terms of where can I use the blue line and not get more than 0.4 worth of error. Just to check, here's error evaluated at 1.3675, and here it is at the upper bound, and you can see they're both very close to 0.4. The lower one is actually a little bit over 0.4, but that's because we chopped it off a little bit low, which means it's outside of the bound. So P5, using contour plot, there's several ways to plot vertical lines, but contour plot is one that works. To plot the two vertical lines at those points, and you can see those vertical lines at those error bounds are exactly where the blue line intersects the lower red shifted function. Here's a larger view of that, and you can see that the actual black function has been shifted down to create the lower error bound for that function, and that the vertical x limits in terms of a lower bound and an upper bound on the values of x, which you can use to not exceed that error if you're using the blue line, it all comes together very nicely. The little red line here is the maximum error. If you go any further to the left, you exceed that. If you go any further to the right up here, you exceed that. And that is one example of a linearization problem.